All right, so I wanted to do a quick little lesson on division, but also multiplication when we're doing it with polynomials. And I think sometimes you can forget this when you get into doing something that's as procedural as polynomial long division, but there is a conceptual side of it too. Remember, there is a relationship between division and multiplication. 24 divided by 6, for example, is 4 because 4 times 6 is 24. So we have to remember that multiplication and division are like two different sides of the road going in opposite directions. Um, you should have done these problems in past classes like algebra, where you're asked to multiply two polynomials. Let's say x minus 2 times 2x cubed plus x squared minus 2x, and you build yourself these blocks, and inside here you're going to multiply this. So I get 2x to the fourth minus 4x cubed plus x cubed minus 2x squared minus 2x squared plus 4x plus x minus 2. And then if you've done this right, what you should see is your like terms are aligned diagonally from each other. So the answer from this is going to be, I'm only going to have one term. I'm not going to have like terms with either my first or my last term. Those ones are going to stand alone. So I get 2x to the fourth, and then I had minus 4 plus 1, so minus 3x cubed minus 4x squared plus 5x minus 2. And that's my answer. Okay, and that's nice, but I thought I'd do one more example here where I have x plus 3 times 2x cubed minus x plus 4. And there is a little bit of a catch with this one. Not sure if you noticed it yet, but let me just go through here, and I'm going to get 6x cubed minus x squared minus 3x plus 4x plus 12. And then when I'm looking for like terms, I notice that these two line up. However, these two right here are not like terms. So there is some kind of problem here, which is not that difficult to reconcile in this case. You could just write this is 2x to the fourth plus 6x cubed minus x squared plus x plus 12. However, when you're going down the opposite way of that street with polynomial division, this is going to be a bit of a problem. And so if you notice, what happened here was I went from x cubed to x to the first, and then you can think of this like x to the 0. When you write a polynomial in standard form, the exponents go in descending order. But if you leave one out with division, with multiplication, and especially with division, you're going to miss a place in that structure. So one way I could have done that, if I wanted to, was just add in a little 0 place, and I would have 2x to the fourth, 6x cubed, 0x cubed, 0x squared, negative x squared, negative 3x, 4x, 12. And then you can see that now in these diagonal columns, I do have like terms, and it does make it a little bit easier. And if I do get a polynomial division problem that's missing a place like this, it's going to screw you up big time if you don't then go ahead and add in a place for the 0. So just forewarning you about that. So let's say I have a problem. This is not going to have one of those situations. In this case, I have 3, 2, 1, 0. So all my terms are accounted for. I'm going to do 6x cubed minus 5x squared plus 5x plus 8 divided by 2x minus 1. Another way that this may be represented is as a rational function or as a ratio between the numerator and the denominator. And in order to do this, I'm going to set this up in a polynomial division format where the denominator goes on the outside of the house. And I do this a lot like I do regular long division. If you think what I need is I need to 2x times something to give me 6x cubed. Well, that's going to be 2x times 3x squared. And then what I do is I multiply 3x squared by this whole expression right there, which is going to give me two terms. And when I do that, I get 6x cubed minus 3x squared. And then this is the trick that I think is helpful. It just speeds me up a little bit to think about. I'm subtracting that whole expression. So I think it's easier to look at addition than subtraction. So one thing I do every time I'm doing polynomial long division, since I'm subtracting both of those, I just change the signs on each term and then I'm adding. So then I get negative 2x squared plus 5x. So then I'm going to get minus 1x. And then I get negative 2x squared plus x. And then I'm subtracting the whole expression, which means I'm going to turn this to plus and I'm going to turn this to minus. And then I'm going to do this cancels, and I get 4x plus 8. And then 2x goes into 4x 2 times, and I get 4x minus 2, and then I minus plus, and I get 10. Okay, and then I'm going to write this as plus 10 divided by 2x minus 1. And if you did a long division problem, like let's say I go 6 goes into, maybe it won't be that long, but 6 goes into 23 3 times, and 3 times 6 is 18, and 5 left over. So the answer to this would be 3 and 5 6. So hopefully you see some analogs for how that works with polynomial division with regular division, even if you haven't done regular division like that since 4th grade. This is your answer. I want to talk in a second about what does this actually mean to have a fraction inside, or not inside, but a fraction to go along with. Like this is just like a regular polynomial expression, and this is a fraction. But the other thing I want to talk about is that there's another way to do this. If you get used to the area model and you remember that division and multiplication are inverse operations, you can use your area model to figure out what your answer is. So basically what I'm going to do is I'm going to put this expression right here on the bottom, and I get 6x cubed and I'm thinking, what are these numbers going to be that get me back here? And if I've done multiplication enough, I'm going to know that there's going to be something x squared, there's going to be something x, and then there's going to be just a regular number, like a constant in there. And I have one extra box. It has way more space. It doesn't have to have way more space, but I'm going to use that extra box. So I'm thinking that I know that this first box has to be 6x cubed, because there's going to be no like terms when I do that. So what would have to go here to give me 6x cubed? Well, that would have to be 3x squared. And then what would 3x squared times negative 1 would give me negative 3x squared. And then I'm thinking these two things are going to be like terms, and they have to give me what this term is down here, which is negative 5x squared. So what's going to go in there? It's going to have to be negative 2x squared. So what's going to have to go here to give me negative 2x squared? Well, that would be negative 1x. Okay, and then that's going to give me plus x. Now I look here. Those two things are going to have to be like terms, and together they're going to have to give me 5x. So what's going to go there? Well, that's going to have to be 4x. So what's this going to have to be? This is going to have to be plus 2. So what's this going to have to be? This is going to have to be minus 2. And now where that remainder comes in is, think of adding an extra term in here that's going to be the remainder. Negative 2 plus something equals this number, 8, right? So what is that something going to have to be? That something has to be 10. So 10 would be here, and 10 would go in my remainder. Now, I said I wanted to think about what does this actually look like. Let's think about what is y is equal to 3x squared minus x plus 2 plus 10 over 2x minus 1. And the first thing we want to notice is that that's just a parabola. Okay, that's not that surprising. What happens when I add in a fraction here? Now my fraction was 10 divided by 2x minus 1. It seems to look nothing like that parabola. Just to show you what the parabola I had before looked like, 3x squared minus x plus 2. It doesn't look that much like that parabola. However, let's think about what is the difference here. The difference is going to be just this part, 10 over 2x minus 1. Well, what's true of this 10 over 2x minus 1? Well, first thing you want to look at when you see a rational function is, or remember that you cannot divide by 0. So in this case, what number would make make the denominator equal to 0? Well, x would have to be 1/2. So when x is equal to 0.5, we get something that's not allowed in that function. This is a thing that we're going to define as an asymptote. It's a value that's not allowed. Okay, and so if you think of what's going to happen with this fraction as you get further and further from 1/2, this is going to matter less and less. Okay, like if you just think of when you put in 100 for x, this is going to be 10 over 200, which is a very small number. So when x gets further and further, either to the right or to the left of 1/2, this part starts to matter less and less and less. So even though it looks like at this point these two functions, this one and this one, are not very similar, if I zoom out, I actually get a picture that shows me that they are kind of similar. And then if I change my scale to account for the fact that y grows much faster than x, in this case, oh, maybe between -8 and 8, you start to realize that this function, the one that I'm showing now, is simply that parabola with a big distortion right where that value x is equal to 1/2, and that distortion is called a vertical asymptote. And we'll talk more about that, but I thought this was a good introduction to that idea of a vertical asymptote.